So yeah, I'm Mike Tynes. I'm a PhD student here at UChicago. I won't tell you what year I'm in, but I'm getting my PhD here in computer science. Um, and yeah, I'll be talking about distributed on-the-fly training of neural network potentials. Let's see if I can hide this. So I didn't realize that the talk before me was going to feature machine learned interatomic potential. So whoever laid out the talks in time did a great job. Uh, so just broadly speaking, machine learning is changing how simulations are done, right? Sort of the old school, right? We have a system in some state at a given time, and we do some accurate but expensive numerical routine and get the next state at the next time step. Generally, the more accurate you want that to be, the more time it takes. In the past few decades, we've been able to machine learn our way around that cost, sort of amortize the cost of doing these expensive subroutines and learn from them, and then use the machine learning to drive future simulations. This paradigm has been applied in a lot of simulation domains. The one I'm most familiar with and I'm working on is molecular dynamics. So we have atoms in space, they have velocities and positions, compute their forces, and then use Newton's equations and those forces to update the positions and velocities just a little bit, take a small step in time, right? And the expensive part of that is computing the forces here. So if you want to do it really well, you're doing quantum mechanics, and that can be cubic complexity, it can be n7th complexity. It really depends on what quantum mechanics you're using. Also, the prefactors on this tend to be pretty bad, and you're limited in your system size, right? You can only have like tens or thousands of atoms. And even then, it can take a really long time. So with machine learning, interatomic potentials or force fields, typically these are linear, and you can get into the billions of atoms on a supercomputer with force fields. So they really are changing the game in molecular dynamics and many other fields. This is the one I know the best. Right, so we've got orders of magnitude speed ups, longer, larger simulations. We do lose some accuracy, and I think more importantly, we lose generalizability to new systems and states. Right, it's possible that the simulation wanders into configuration that your machine learning really just wasn't prepared for. So a lot of the work that I've been doing lately has been focused on identifying those situations and correcting the machine learning when we need it. So this paradigm is on-the-fly learning. So instead of just running our machine learning at every time step, we're in our state at some time, t here. At every step, we ask, do we trust the machine learning? If yes, then we just use it and get our next state. If no, we run that accurate, slow numerical routine, use that to update or retrain the machine learning model, and then propagate in time. And I have a decent amount of work I've done in this space. This is actually previous work that I was not involved in, but built on. But this is maybe a little bit more fundamental. This idea of using a controller, right? So at every time step, when we ask, is the machine learning trusted? We have some uncertainty quantification, that's UQ threshold, and that changes over time based on the errors that we observe. So every time we run the accurate slow routine, we can compare and see how our machine learning is doing, right? And then we know how wrong we really are, so that helps us calibrate our uncertainty metric, right? And the user provides this error tolerance. And by dynamically adjusting this UQ threshold, we can basically force the average errors over time to fall within this tolerance. So that's all great, and it works really well. Balances this cost and accuracy trade-off nicely. But training these models in serial sort of really limits what models you can use. If you're going to be training at every time step or every 1,000 time steps that you're wrong, you can't use a model that's going to take hours and hours to retrain. You're going to lose your whole speed up, and it would be a lot more efficient. Use that compute time more effectively in a distributed setting. So that's actually what I'm going to be talking about next, rather than some of the work I've done. This is sort of the work that I'm currently prototyping and moving towards, and this is like where Parcel and Globus Compute and Colmena and Academy are going to come in, right? So we're starting with some set of initial configurations, systems of interest that we want to simulate, and I'm assuming for the purposes of this talk that this is basically a bottomless pit of configurations, right? And we have, okay, these are all agents. So the colored boxes are autonomous pieces of code that could be executing on one computer, they could be executing on many computers, and they're performing their little tasks and passing data to one another. And that's done through the prototypes in Colmena. We may be moving to Academy. These are both sort of agentic workflow tools that are being developed in Globus Labs. So if you have questions about those, there are people here who can answer better than me, although I can try. But broadly speaking, right, we have this dynamics engine that's using machine learning surrogate, propagating systems forward in time, so some chunk of time. We have another agent that's looking at those trajectories and asking, do we trust them or not? If yes, we can propagate them further in time. If not, we'll sample training data from them. So the training sampler will pull out training data from those trajectories or maybe generate new training data that's similar to the frames where this thing went wrong or where the auditor thinks it went wrong, right? And then we send those maximally informative frames to the training labeler who's going to actually run the expensive quantum mechanics, right? And send that to a training database. Then we have a trainer that will train new models and periodically push them out, emit them, and the dynamics engine will pick them up at some point. So how much time do I have, Yadu? Okay, perfect, right? Again, we're in the prototyping stage where all this is running in a Colmena app locally, but we have a few visions for how we'll do this at scale, right? The training and the labeling are really the most expensive parts. I'm not really going to talk about the dynamics engine. That's pretty fast. These are the slow parts, right? The training and the labeling. So a lot of these quantum mechanics codes are really CPU heavy, and the machine learning is obviously better to run on a GPU. So we may be in a situation where we're running a multi-site workflow, in which case Globus Compute is going to make the most sense. If we're running on something like Perlmutter, where we've got a nice GPU and CPU partition, we may just be using Parcel. But yeah, we have some challenges with large data movement, multi-site workflows, fault tolerance. There's also high variance in the task times, right? Could easily spend weeks or months just labeling data. We don't want to end up there. But we're envisioning days to week-long campaigns. So that's some of the challenges I anticipate facing. And I'll open the floor to questions, comments, suggestions.